Ladies and gentlemen, welcome to this lesson, Chemical Equilibrium, lesson number 2. If you haven't subscribed to this channel, make sure that you subscribe, you press the notification button so that whenever we post a video, you get notified. Support local YouTube, guys. This YouTuber is based in Malamlele. So if you are watching these videos coming from Gauteng or elsewhere, just know that at Malamlele in Limpopo, this is how we do it. Thank you very much. In lesson number 1 for chemical equilibrium, we explained quite a lot of things. We explained how to determine whether a forward reaction or a reverse reaction is endothermic or exothermic. We also indicated how temperature favor the endothermic reaction and how the decrease in temperature favor the exothermic reaction as the increase in temperature favor endothermic reaction. We have demonstrated quite a lot of things. If you haven't watched it, make sure that you go and watch that channel. I encourage you that please share the videos, share the links of our YouTube channel with your learners, if you are a teacher, with someone, because these videos, they're quite helpful. They are assisting a lot of kids to pass so that South Africa can be a country full of educated people, and that's the goal and the aim. We want to educate the black nation, want to educate our people so that they change their lives and we eradicate poverty. You know that next week it's election week. We wish that you go and choose the correct government which will take South Africa forward. Thank you very much. We are continuing with chemical equilibrium. Chemical equilibrium. In this lesson, we'll just touch on the parts that we left out in the lesson number 1. But we're going to introduce something new. We're going to focus on the equilibrium constant. We talk more about the equilibrium constant. Okay, thank you very much. I will start by demonstrating to you other ways in which we are able to see which reaction is being favored. You know that from the lesson of last week, where we have the time, and here we have we can have the moles or the molecules. If we have a straight line and we have 2 lines with the key where the broken line and the solid line, broken line represent a reverse reaction, while the solid line represent the forward reaction. So I've already indicated to you that these 2 parallel lines, they mean that the reaction is at equilibrium. It means the reaction is at equilibrium. In a situation where you find that the solid line started to increase and the broken line start to decrease, it will mean that the forward reaction is being favored. The forward reaction is favored because the forward reaction as represented by the solid line is showing an increase, meaning that we are having an increase in the number of moles as I indicated here. So this broken line is decreasing. It shows that the reverse reaction is not favored. So this is what I demonstrated to you, a simple way for you to be able to see which reaction is favored, whether it's a forward or a reverse. But there is the second part which it is important for me to demonstrate to you, how to perceive which reaction is being favored or not. I will still use the same information. We've got moles we've got time. In a situation whereby you find that we have this, we've got these, both of them, they get to decrease. We have a sudden decrease like that. Then, because this decrease indicates that equilibrium is disturbed. Equilibrium is disturbed. Then we have this. Then the reaction comes back to equilibrium. It establishes a new equilibrium. Then, in a situation where you find that the broken line is decreasing, but it does not reach where the solid line reached, it just decreased to a certain extent, then it comes back. It comes back to normal. When it is like this, you can see that both of the graphs, they are decreasing. Both of them are decreasing. But we cannot say that both of them, they are not favored. Both of them, they are not favored. It is not true, because there is a disturbance. Whenever we have a disturbance, one reaction is going to be favored and the other is not going to be favored. The only time whereby both of them are being favored is at equilibrium. Remember that at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. I can boldly say that at equilibrium, both the forward and the reverse reaction are being favored. But in a situation where we have a disturbance, this disturbance which have caused this straight line to shift, and you can see there is a decline in the number of moles. One reaction is being favored. So how do we know which one is being favored? The reaction that decreases less, it is being favored, and the one which decreases more, it is not favored. It's another way of determining which reaction is being favored. I hope you have noted that a reaction that decrease, a reaction that decrease less, a reaction that decrease less is favored. Is favored, right? A reaction that decreases more is not favored. So this is another way of determining which reaction is being favored. I hope you are understanding what I'm trying to demonstrate to you. A situation whereby both of them, they are decreasing, but one reaction decreases more. It means that the one that decreases more is not favored. You can see that the solid line, it has reached this part. Then the broken line, it is somewhere around here. It decreases less. The number of moles of the reverse reaction is indicated by this key. They are more than the one of a forward reaction of a solid line. So that's one of the things that I left out from lesson number 1. I hope you understood. If we have two reactions, forward and a reverse reaction, and you find that one reaction is decreasing more, the other does not decrease as much as the first one, it will mean that the one that decreases less is being favored. Then the one that decreases more, it means it is not favored. So that's how we determine which reaction is being favored or not. Ladies and gentlemen, sometimes they give us questions whereby we need to explain the endothermic and the exothermic in terms of color change, whereby we need to explain in terms of color change. If you check the Limpopo June exam, as I'm from Limpopo, I promote Limpopo, and you know that Limpopo is one of the provinces that is leading in terms of maths and science. Overall, other provinces, they can beat Limpopo, but not in maths and science. Even in universities, we are dominating in Limpopo. So if you check a question from Limpopo June, the examiner of Limpopo does not play. The Limpopo examiner, it will crack your head. I say it's good, it's bad, it's good, it's bad. I don't know how to explain that one, but the questions that the examiners set for Limpopo, they are rich. Learners need to crack their head, and it's good. It gets to test us teachers if we are really teaching or just teaching question papers. Okay, I want us to do a question. We'll just focus on color change. We'll just focus on color change. I just want you to understand. It's Limpopo, June 2023. The question says, a solution of cobalt chloride in ethanol is blue owing to the formation of the ions. If this solution is diluted sufficiently with water, it turns pink because of the formation of the ions according to the reversible reaction. Okay, I want to show you the issue of color change. Let's say we are given a reaction which is COCl4 2 minus plus 6H2O. It is a reversible reaction. Reversible reaction, it means it is able to reach equilibrium. Remember that a reaction that is not reversible, it cannot reach equilibrium. Then we are given that the enthalpy is less than 0. What does it mean? It means that this reaction is exothermic. And I told you from lesson number 1 that whenever we say this reaction, we are referring to the forward reaction. So this key talks to the forward reaction. It means that the forward reaction is exothermic. Whenever we say this reaction is exothermic or endothermic, we are referring to the forward reaction. I want us to check. We are given a key. We are told that this one is pink and this one is blue. The first one is pink or blue. Okay. So I want us to answer only one question. I want us to answer only one question and see what will happen. Let us look what's going to happen. Let me read the question again. It says that a solution of cobalt chloride in ethanol is blue. Solution of cobalt chloride is blue owing to the formation of the ions. If this solution is diluted sufficiently with water, it turns pink because of the formation of the ions according to the reversible reaction. The reversible reaction is this one that we are given. Then 6.1.1, I just want to focus only on color change. Then I continue to teach because this lesson is for teaching content. It's not answering question paper. We'll have lesson number 3 where we are just dealing with treating question paper. You will notice that our videos, they are not just based on answering question papers. They are much more based on teaching you the content so that you can understand. We know that these days the grade 12s, they are no longer given much time to repeat if they fail. We have a lot of people who are writing supplementary exam. We've got a lot of people who are not having the opportunity to be in class. So these videos are targeting such people so that they can be able to catch up and learn outside the class using this nice technology. So, okay, 6.1.1, it says, what will you observe in each case? If the pink solution is heated strongly, the pink solution is heated strongly. When we heat something, what are we doing? It means we come to the pink solution and we increase increase temperature. Can you see? We come to the in solution and we increase temperature. Then when we increase temperature, that's what this is what we're going to observe. Isn't it? They say if the pink solution is heated. So if we heat something, it means we're increasing its temperature. And what does that mean? Remember that this reaction is exothermic. It means that the forward reaction is exothermic. Forward reaction is exothermic. So what do we do? It means that a reverse reaction is endothermic, because in lesson number 1, I indicated to you that if forward reaction is exothermic, then reverse is endothermic. If forward is endothermic, then reverse is exothermic. That's what I've indicated to you. So for this reaction, forward reaction is exothermic. So when we increase temperature, it will favor the what? It will favor the endothermic reaction. When we increase temperature, it will favor the endothermic reaction. And in this case, the endothermic reaction is the reverse reaction, meaning that pink will turn to be blue. So this is what is going to happen. So the answer there, the pink color will become blue. Why is the pink color becoming blue? It's because the reverse reaction is going to be favored as we increase the temperature, as the reverse reaction is what is endothermic. So when we heat pink, we're increasing temperature, we will favor the what? The reverse reaction. And in this case, reverse reaction is the endothermic reaction. How do we know? It's because the forward reaction is exothermic. That's how we know. We're given this key that forward reaction is exothermic. As I've indicated that this key talks to the forward reaction. Okay, I hope you understood. I know you always come across questions that addresses color changes. So that's how we get to determine the color changes. That's how we determine the color changes. So let us come to something else. We're going to something else now. We're coming to something else. Ladies and gentlemen, if you are given a chemical reaction like this, A reacting with B, and then it forms C and D. You know, that's how I usually write. If we have S, this S is a phase of substance A, it means it's solid. S stands for solid, and we have a G here. This is a gas. Then we have a L. Let me write, I'll write L. Then we have AQ. This is for the sake of teaching you. So this is a solid. S is for solid. G is for gas. L is for pure liquid. Pure liquid such as water. Then AQ is for aqueous. Is for aqueous. AQ. So these are the phases. And these phases are very important when we talk about equilibrium, and we talk about equilibrium constant and everything, the phases. What I want to tell you is that solid, something that is in solid phase, and a pure liquid as in air. Solid do not affect equilibrium position. Solids do not affect equilibrium position. Solids do not affect equilibrium position. We can even say solids do not affect Kc. I'm writing Kc so that I don't forget to teach you. Remember, I didn't explain to you anything about Kc, which is the equilibrium constant. So yeah, you need to notice that a solid does not affect equilibrium constant. A solid does not affect the equilibrium constant. A solid does not affect equilibrium constant. So you need to take note of that. Okay, so If you can be given a question like this, if you can be given a question like this, you are given a chemical reaction, sodium carbonate, calcium carbonate, solid, which is reacting with, which is dissociating. It's not reacting, it's just dissociating. Okay, and this is a solid, and this is a solid, and you can see the product there. It is producing carbon dioxide. It is producing carbon dioxide, and sometimes they will give you a reaction like this, and they will not give you the product. They write X where there is a product, and they will require you to tell us the gas, that is the gas which is being produced, and you can see that it is producing carbon dioxide. You can see we have oxygen, we've got carbons here, we've got carbon. So that's one of the things you need to take note of. But here, what I want to demonstrate to you is that if this reaction reaches equilibrium, you can see if this reaction reaches equilibrium, right? Let's say it have reached equilibrium, then we increase the calcium carbonate. What is going to happen to equilibrium? Nothing. Equilibrium will remain the same. Why is equilibrium remaining the same? Is because solids do not disturb equilibrium. Solids do not affect equilibrium. So it's something you need to take note of. Solid cannot be affected by equilibrium. Solids does not affect equilibrium. The same applies to if a reaction reaches equilibrium and they say that they increase the surface area. Surface area is not going to affect equilibrium. Remember, the factors that affect equilibrium is temperature, pressure, and concentration. Those three are the ones that are going to be able to affect equilibrium. So yeah, it's one of the things to take note of. I hope you can see. Ladies and gentlemen, let us talk about Kc. Let us talk about Kc. There is what we call Kc. In acid and base, we call it Ka and Kb. That is the equilibrium constant of water. Okay. So Kc is what we call equilibrium constant. Equilibrium constant. Kc. So the equilibrium constant, you need to take note that it cannot be affected by solids. Solids do not affect equilibrium constant, and pure liquids. Equilibrium constant cannot be affected by solids, and it cannot be affected by pure liquid. In this part, we'll be dealing with calculations. We'll be dealing with calculations. The formula for equilibrium constant, Kc, is given by the concentration of products over concentration of reactants. Concentration of products over reaction of reactants. Let me crush it. The reason I'm crushing it is never ever express the formula like this, because you will not get a mark. You need to be specific when you express a formula. You need to be specific when you express a formula. Don't write concentration of product over reactant, but that's what it is. You need to express it according to the reaction that you are given. If, for instance, you are given this reaction, A react with B, forming C and B. When you express your Kc, you're going to say Kc is equals to concentration of C, you multiply it with concentration of B over concentration of A, multiply it with concentration of B. Can you see? This is the formula that you are going to get a marks for. But if you write concentration of product over reactants, we're not going to mark you because you haven't said anything. When you write this, yeah, now we are talking. You understand? So you need to always be specific. The formula for Kc, which you are going to receive a mark for, must be specific, must address the given equation. You understand? So this is how we express the Kc. So I cancel this not because it is not correct. It is correct, but I know you learners, you love writing this and it is incorrect. So please avoid making such mistakes. I hope you are following. Then, ladies and gentlemen, let us expound on this Kc. What is happening with Kc? While we are still expressing the formula of Kc, if we were having this reaction, A reacting with B, forming C and D, you find that we need to balance this reaction. The reaction is balanced like that. This is an example of balancing. You can see that we've got a 3 and we have a 2 and a 3, which has stoichiometric coefficients, which are used for balancing. We say this is a balanced chemical reaction. We need to express the Kc for this given chemical reaction. We are going to write Kc is equals to concentration of product. What is the first product that we have? The first product that we have is C. You can see that there is no stoichiometric coefficient, so we're not going to write anything, just going to write C as it is. But this time around, we've got the second product, which is D, but there is a stoichiometric coefficient of 3. It means we are going to make that 3 to become a power. So the stoichiometric coefficients, they must be powers. We use them as powers, as exponents. Then we have the second part where we are expressing concentration of reactants. We have A reactants which have got the stoichiometric coefficient of 2. Then we're going to write 2 as a power. Then we have B. So this is how we express our formula for Kc. As you can see, this is how we express our formula for Kc. So this is the only trick when it comes to expressing the formula. Oh, I'm thinking of something to also indicate to you. Okay, let us move forward. You know that the solids and pure liquids, they do not affect the equilibrium constants. You know that the pure liquids and solids do not affect the equilibrium constants. Let's say we have a reaction like this, A2, this is S, you can see it's in solid phase. Then we add it with B. We add it with B, which is a gas, Then we form C plus D, which are both gas, and then gas like that. Okay, to avoid a lot of things. Let me make it a gas. You can see we've got a solid, a gas, and a gas, then the gas again. You can see. So we need to express the Kc for this given equation. Let's take I have a 4 here. We say this is a balanced equation. This is a balanced equation. Notice I'm giving you ideal equations. These equations that I'm giving you, they are not real. They are just ideal. Okay. So if we want to express the Kc value for this one, remember that solids do not affect Kc. It means solids are excluded on Kc. Solids are excluded when we deal with Kc. We must not include the solids. Solids are excluded when we're dealing with Kc. So it means if we want to solve Kc for this one, I'm going to say Kc is equals to concentration of product. What are the products? What are their phases? They are gases. Gases are included. We only exclude solid and pure liquid. Pure liquid, the one which is going to be represented by L, it means it's a pure liquid. Then it means we are going to say C to the power 4. Remember I told you that the stoichiometric coefficient, they must become powers. We multiply it with D. You can see D does not have a stoichiometric coefficient. Then we divide by reactants. Reactant, we have only one, that is B. We have B like that. Let me write in the middle. We've got B like that. Why are we not writing A? A, we cannot include it when we calculate Kc because solids do not affect Kc. So we cannot include A. We cannot include A because solids do not affect Kc. Okay, I think you are understanding. That's how we do it. Okay, let me do something else. Let's talk about Kc even more. How does temperature affect Kc? What is the relationship between Kc value and temperature, endothermic reaction, exothermic reaction? Because the endothermic reaction and the exothermic reaction, then Kc, those things, they are related, they are working together. Okay, let us talk about temperature. Listen, increase in temperature, right, means that Kc value will be high. Increase in temperature means that Kc value will be high. Let me informally say that temperature is inversely proportional. Temperature is inversely proportional. Not inversely. Directly. I'm sorry. Temperature is directly proportional to Kc value. Yeah, this statement I think is best. But don't write it. Explain it in words. Just explain in words. What does it mean? It means when temperature increase, it means Kc value increase. When temperature increase, it means that the Kc value is going to increase. What does it mean? It means when Kc value decrease, it means temperature is going to decrease. When Kc value, when temperature decrease, Kc value also decrease. Of course, we know that Kc value, it is not the one that is affecting the temperature. It is the temperature that is affecting the Kc value. Okay, so I will write this so that you don't forget. It's the best way to write so that you do not forget. Don't write it as it is. Explain in words that when the Kc value is high, it means if the temperature is high. when Kc value is low, it means even the temperature is low. So that is the relationship between Kc value and temperature. So sometimes you come across question that what will the Kc value do to the Kc? I mean, what will the temperature do to the Kc? What will the temperature do to the Kc? So when the temperature increases, it means even the Kc value is going to increase. So that's how we get to determine when the temperature increases, it means even the Kc value is going to increase. So that's how we get to solve these things. Then let us talk about endothermic. Let us talk about endothermic. It means that, it means that larger, when the Kc value is large, it means higher temperature. Higher temperature favors what? Favors endothermic reaction. Higher temperature favors endothermic reaction. We know that when the temperature is high, it means that the endothermic reaction is favored. It means also higher temperature also favor what? Favors the high Kc value. It means when temperature is high, the Kc value is going to be high. You understand? Okay. We can ask a question. What does high Kc value means? When the Kc value, what does it mean? It means that we will have an increase. We'll have an increase in production. It means in production or yield. When the Kc value is high, it means we're going to have a high production. We're going to have a higher yield of whatever that we are producing. Remember that these reactions, they are being performed in industries. And in these industries, we are interested in the products because we are selling the products. If you are a chemical engineer, you are interested in the products. You just go there and you want a high production. So you will make sure that the Kc value is high so that the product can be produced at a high level. I hope you understood what I was trying to demonstrate to you. What does it mean? It means lower temperature. What does lower temperature do? Favors the exothermic reaction. It favors the exothermic reaction. When the temperature is low, exothermic reaction is favored. You are with me? It means we're going to have a low Kc value. A low Kc value. A low Kc value. When we get a low Kc value, it means we have got the what? An exothermic reaction. A lower Kc value means we have an exothermic reaction. We can even write it alone. Lower Kc value. Lower Kc value means we have an exothermic reaction. Lower Kc value means we have an exothermic reaction. It means a larger Kc value means we have an endothermic reaction. Yes, you can say that. A larger Kc value means we have an exothermic reaction. Lower Kc value means we have got what did I say? Larger Kc value means we have endothermic reaction. Larger Kc value means we have endothermic reaction. I'm sorry if I happen to say some wrong thing. Let us correct. When the Kc value is larger, it means we have an endothermic reaction. When Kc value is lower, it means we have got the what? An exothermic reaction. So that's how we get to relate the two. That's how we get to relate the two. Larger Kc value, it means we've got the endothermic reaction. Smaller Kc value means we've got exothermic reaction. So that's how we get to determine how this Kc value affect like how it is affected by temperature. When temperature increases, it means the Kc value is going to increase. That's how we get to determine how Kc value is affected by temperature, and the larger Kc value will favor endothermic reaction. Just before I conclude, let me just demonstrate something to you. This is just a way of trying to see if you understood what I've been teaching or not. Let's say we have this reactant. These reactants, okay, A in gas reacting with B in gas, forming C gas and D gas. You can see this is a reaction. Can you see? It's not a reversible reaction. Then we make it a reversible reaction by drawing the two arrows. It's now a reversible reaction, meaning that this reaction can reach equilibrium. Then if I say, if I increase B, if I increase B, what will happen? If I increase B, what is going to happen? If I increase B, what is going to happen? Let us write, according to Le Chatelier's principle, remember that the reaction that is going to oppose the disturbance is going to be favored. What is the disturbance? Disturbance is the increase in B. So it means a reaction that is going to oppose an increase in B is the one that will be favored. So which reaction is going to be favored? A forward reaction is going to be favored. But that's not the answer for the question that I asked. The forward reaction is going to be favored. What does the forward reaction do? The forward reaction causes the production of C and D, which is the product, right? So what's going to happen if I increase B? It means that C plus B increases. It means the products are going to do what? To increase, because we've increased the reactants which are used to produce the product. So when we increase the reactants, it means we're going to have more products. But what's going to happen? A plus B decreases. A plus B decreases. So A plus B is going to decrease. These reactants are going to decrease. These reactants are going to decrease. So that's how it works. These reactants are going to decrease. Are going to decrease. So sometimes in a reaction, you find that it's in a library, not a lab, maybe in a chemical industry, not a lab, because whenever we talk about real chemistry, we will be doing whatever that we'll be doing in the industry, in the company, just like Sasol. Okay, so let me show you this. In a reaction which is being done in the industry, you find that they are using they are selling D. They are selling D. Remember, when we perform this reaction, sometimes we perform other processes, different reaction to produce manure and different things which we can sell in different companies. So how is the rate of reaction used? And they are selling D, right? Meaning that whenever they perform a reaction, what do they do? Whenever they perform a reaction, they will make sure that they produce a high product. They'll make sure that they produce a high product. So what can they do? If they want to produce a high product, it means If I remove D, remember that D is a product, right? So if I remove D, what's going to happen? A reaction that is going to oppose the change is going to be favored, right?